and we're going to open up a new model. And you're actually going to tell me, how do I open up a new, an entirely fresh new model? Who could tell me how to do that here in AnyLogic? File, new, that's right, new model. And we're going to call this first SIR model, okay? And we're going to make its time unit days, and I'm going to put it in a favored location for this boot camp. Okay. Okay, so ladies and gentlemen, the first thing we're going to do, as is often the case, is we're going to build up a model with that includes people as part of it. If you want, you could name yours your favorite veterinary specimen. But I'm going to add in a person class. Can you remind me, how do I add in a person class to this model? How would I add in a theory of personhood to the model?
Go to palettes.
Yep.
Click on agent type.
Yep, you can do that.
And then drag across.
Good. So we could go. You could go create an agent type, and this will actually allow you to choose with several options, including to create a population of certain types of agents, and you can name them, and you can actually, in fact, use a template. I'm going to show this from scratch because that auto-wires some things. I'm going to right-click here, do new agent type, and person is going to be the agent, okay? And this person agent, we're going to represent once again with a simple circle, okay? So what I'd like you to do is to go give this person a circle representation. How do we do that? Where do we go in the model to give them a circular representation?
Presentation?
Yeah, we go to presentation for person, right? And person was probably directly opened up. So we're going to go to the presentation palette, and we're going to drag in a circle. And again, you can futz with it visually. My own preference is to just go down and set the radius to be 10 here, okay? So we're going to have this radius. Actually, I'm going to set it to 5 so we can have a little bit better use of screen real estate. A size of 5, okay? Okay, next, ladies and gentlemen, we're going to add in a population of people. How do we do that? How do we add in a population of people? Does anyone remember?
Add a parameter.
Yeah. Okay, we will add a parameter. The parameter will add to main. It's going to be called population size. So let's go do that. We're going to add in a parameter called population size. And what sort of parameter will that be? Will it be a double? Will it be a Boolean? What sort of thing will it be?
Integer.
It's an integer indeed. It's 0 or 1 or 2, etc. So it's confined to be integers. Okay? So we should say type integer, and we'll give it a value if nothing is specified for it in an experiment. It'll be a value of, say, 250. Okay? 250 people in this population. Okay, so ladies and gentlemen, I'd like now to go and actually add in the population of people. So we have a population size, but for what population is that For what population does that size apply? Well, we need to create a population of people. How do we do this? Anyone remember? This is a common task. You've only seen it once before, so it's no shame to not remember, but does anyone happen to remember how you add that in?
Copy.
Yeah.
Copy person.
So we drag in person over here, and we call it population. And is that all that's needed to make it a population? No, in fact, we have to say it's a population of agents, and the initial number of agents will be what? Population size, indeed. Yeah, exactly. Okay. So population size. Okay? There we go. Good. So that's excellent. Okay. So we want to have this appear visually in a way that's clear, and that's not going to be the case now. If we run this now, what will we see? Anyone remember from this morning? What would we see?
Just the white dot.
Yeah, we'd see the white dot. That's right. Okay, so it would just be a single white dot on the upper left here. And what is the population size here? If we drill down, there'd be 250 people, but they're all atop of one another. So in order to make them clearly visible, what do we have to do?
Go to initial location.
Yeah, exactly. And that initial location lives actually in the population, okay? We can go set their initial location to be in the specified point, and it'll be uniform, say 0 to 500 and 0 to 500. Okay. So, ladies and gentlemen, okay, so I'd like now to go and try running this. So what did I do? Just to be clear for those following along, I went to population, went to initial location. Here said in the specified point, and the X is uniform 0 to 500, the Y is uniform 0 to 500. Okay, let's go run this now. And you should see something like that. Do you see that? Who needs a bit of help? I'm happy to help. Anyone need me to come by and look? No? You're seeing that? Okay, good. Great, okay. Now we are going to veer off in a radically different direction from this morning. From this morning, we confined ourselves with adding some heterogeneity to this population. And that's a critical component for a lot of models, but it lacked dynamics. It lacked behavior over time. And it's to that task that we now bend ourselves. Okay? Okay, so ladies and gentlemen, we're going to go to person here, and we are going to add into this person a state chart. Okay, and this state chart will be an infection state chart. Okay, in this infection state chart, we're going to have similar sort of categories for what we saw this morning, except that we're going to have an exposed category as well. Okay? So, ladies and gentlemen, I'd like you to go and we're going to go add a state chart. In order to do this, we need to go to the palette, and we go down to the state chart area. Alternatively, we could go to the agent area where state charts are also visible, but I'd suggest going to the state chart area. Okay, of the palette, and make sure person is open. And now we're going to add in elements of a state chart. So we're going to add in state chart entry point. Okay, and this will be called infection state chart. reflecting the fact there may be many state charts which capture different concerns regarding an individual. Okay, so we have an infection state chart, and initially we're going to add in two simple states. The first of them will be susceptible, and the next, ladies and gentlemen, will be exposed. Now, we need some way of transitioning between them. And in order to do that, we're going to add in transitions going each way. I'm going to add in a transition here that's going to represent infection. Notice when I'm, that's exciting. Okay, it's going to call infection, be called infection, and you notice there's a little square here that says show name. You're going to want to click show name so that you can drag a nice name next to this. In general, it's good practice to label your names. You'll notice there's another one which is very useful sometimes called ignore, and that can be used to sort of disable features of models when you don't need them if you wish to do so. Okay, so ladies and gentlemen, infection as shown name, and we're going to leave its properties as such for the moment, and then we're going to drag one going back from exposed to susceptible, which is going to be called, for now, it's going to be called recovery. Okay, and we're going to change this in a few minutes, but for now we're going to use this trivial state chart. After all, we're going to walk before we can run, and we want to show some behavior associated with agents. Okay? Okay, so ladies and gentlemen, let me show the state chart in all its glory. There it is. To be clear, I added this entry point. Notice that should be distinguished visually. It's not the same as this initial state pointer. It's this entry point. It's this bar there. It comes down to susceptible, you have exposed, and you have this here. I checked show name and did not modify the properties, and same thing here. Okay, now what do you think will happen if we run this model right now? What will be, so this expresses some sort of theory of the world, or theory of a world. It's sort of a description of how things could work in some world. What will happen in this world if we were to look at what was going on? What lies beneath the surface of this appearance of peace here? What if we were to go down to each individual? What would we see? Do you see what I see? Yeah. So they're going back and forth in a very specific way. If we would look at each particular individual, they're actually behaving very similarly. You'll notice this is showing sort of the time until this transition is going to fire, etc. Okay. Notice, incidentally, we did not check show name for this one, and I should have. And by virtue of showing the name, it also shows some statistics there associated with it. That would have been a more wholesome thing. Okay, here we go. Okay, there it is. Okay. So we're showing each individual is oscillating. In short, ladies and gentlemen, it's not to be dismissed. We've added state and we've added behavior that operates in that state, processes that operate in that state. That's not a trivial thing. It's a thing of significance. But, ladies and gentlemen, I'd like to make it less cumbersome to inspect what's going on. So, ladies and gentlemen, I will ask your indulgence by putting in place some additional mechanisms so that we can see with the clarity afforded by visualization what's happening without having to dive down and see it manually. So, ladies and gentlemen, I would like to associate each person with a color so that their color of their circle changes when they change state. Okay? And I'd like you to follow me in this. For the susceptible state, I'm going to make them green. And by convention, I'm just going to color this state green to denote that it's associated with that. And the fill color here is going to be, I'm going to make it yellow, meaning they're exposed. We'll be adding an infective and we'll be adding a recovered, and each of them will have successive colors. So I've just done susceptible and yellow, but by itself that does nothing. That doesn't by itself, that doesn't change. I mean, it's a useful communicational tool for what's going to come, but it doesn't change anything. To change something, ladies and gentlemen, we need something more. We need a way of the state chart communicating with this oval as to what color it should be. Now, there's two ways to go about this. One way would be for the oval to ask, in terms of determining its color, what state am I in? And we could do that, but it gets cumbersome for large numbers of states to do in a direct way. Instead, what I'm going to do is I'm going to use a trick, which is we'll see later, possibly later today, certainly later in this boot camp. I'm going to add a variable, and this variable will be called color. Okay? And because we're in the States, I'm not going to spell it with a U. Okay? It's going to be called color with just an O. To Canadianize, it looks bereft. Okay. This is going to be of type other, and its type will be color with a capital C. Now, this capitalization is important. Ladies and gentlemen, we unfortunately live within the tyranny of case sensitivities of Java. So the fact that this is capital C color and this is lowercase c color for the variable name, but capital C color for the type is very important. Capital, do you remember what I said this morning? When we give something a name capital, like person with a capital P, sex with a capital S, color with a capital C, what does that indicate? It indicates, ladies and gentlemen, color hood. It indicates a set of possible colors. Set of possible colors. So this type, just as you can have a variable like population size that has a type int, which indicates it can take on any integer. This variable c with a lowercase c color can take on any of the colors that are included in capital C, which is a huge variety of different colors, including some of whose name I am yet innocent. So this lowercase c color is a variable that will have one of these colors as specified by capital C, just as in main, the population size, if we went up to main, population size can take on, this population size parameter can take on a specific int associated with it. In any run of the model, it will have a specific int, and for any given person, they'll have a particular color in lowercase c color. Does that make sense? Okay, ladies and gentlemen, having done that then, we are going to assign a color to that variable. So when they're susceptible, we're going to assign that color to be green. Green, okay? Now, for the first time, you are seeing a hallmark of the tyranny of Java. And I regret to convey this to you, but it's an important point. See this semicolon. Okay, Java, like other languages in its families, is afflicted by cancer of the semicolon. And basically, whenever you give it a command, you tell it, do something. Not you're giving it a value. You're giving it a command. You're saying, do this. You need a semicolon after it. That's called a statement. It's like a command. You're telling it, do this. Here, the entry action is saying, what should I do if I enter this state? When I come into this state, what should I do? And you're saying, do this. So you need a semicolon after it. If it were merely asking for a rate, for example, you don't need a semicolon after it. You're just giving a value. But here you're saying, do this thing. Make this change. Make this happen. So you need a semicolon after it. That is when you need semicolons, when you're giving a command, a statement in Java. By contrast, we're going to see if you specify a value, if it's looking for a value for this timeout, you don't need any semicolon here. This would be a mistake. That would be a terrible mistake because you're not giving it a command, you're just giving it a value. Here you're giving a command, so you have to say that. I'm sorry, but you'll see this reinforced again and again. So now, ladies and gentlemen, for this, can anyone tell me what you have to say here? If we want to set the color to be yellow here, what do I have to say? Color equals yellow followed by what? Semicolon indeed. Okay. Now, I will tell you that occasionally AnyLogic allows you to get away without a semicolon because it will insert one automatically for you secretly. But as a general rule, always put in a semicolon if you're telling it to do something, giving it a command, but not a value. If it's asking for a value, you don't need any semicolons. Okay? Okay, color equals yellow. So color equals green here while they're in this state. Color is green while they're in this state. Color is yellow. Okay? Okay. Ladies and gentlemen, the final thing we have to do is actually make it their color, the color of this oval. So if we want this color to be the color of this oval, where do you think we need to go? Who do we need to talk to? The oval indeed. So here we go up to the oval, and for the fill color in the oval, we need to set its dynamic value. We need to set it to a dynamic value, not some fixed value of color, to a dynamic value, and its value will be color with a American spelling. Okay, so that's referring to the whatever value of color is in here, which is one of the values of the capital C color. Whatever particular value of color is there, make that the fill color of the oval. That's what that's saying. Just like in that later model, that earlier model, remember we made the radius depend on their income. Remember we made the color depend on their sex. So it is. It's depending now on a variable. And this variable, unlike their sex, can change over time. Okay, at least unlike in the model. Okay, so now what do we see? Why do we see this? It looks like fireflies in certain rivers in Southeastern Asia. Yeah, there's this loop at the level of an individual, and these are based on timeouts, ladies and gentlemen. These are based on timeouts. The timeouts are fixed. They're time exactly 1 day. Okay? Ladies and gentlemen, I'd like to now set this to be a rate. Okay? This will be based on a rate. It's a hazard rate. Same average time in that state. 1/1 day. That's the same average amount of time as with the timeout. But now it's a probabilistic thing. It's not some fixed time. Now it's a memoryless process. Your chance of leaving in the next little bit of time is the same no matter how long you spend in the state. Here, previously with the timeout, you stayed, it matters entirely how long you've been there. You stay exactly 1 unit of time, 1 day. With a rate, your chance of leaving is independent of how long you've been there. If you're still there, your chance of leaving the next little bit is independent of how long you've been there. It's memoryless. This is associated with an exponentially distributed time. It's a hazard rate. Okay, ladies and gentlemen, suppose we put that into place. Would that lead to the same blinking? What will we see now? Okay. Ladies and gentlemen, so now they're desynchronized. Why? Because they're leaving to the exposed state at different times, and therefore they're getting back, even though the return is 1 time unit later, they're getting back. They're staying exactly 1 time unit still in the exposed state. We could change this to be a rate if we wanted to, and then then some of them will be spending longer time exposed, some lesser, etc. Okay, ladies and gentlemen, here we go. Okay, so that's very good. Okay, so we just added some dynamics to our model. We have people going between two different states. That's good. That's good. We also have visual representation of where they're going. Let us, right now, ladies and gentlemen, let's go put some statistics on this. Now, those of you who are here for the very beginning part of this of the session will know where statistics live. If we want statistics to be computed for our population, where do we need to go? To our population, indeed. So let's go to our population. And I'm going to bring this around. You notice when you select things, often these things get highlighted and you can kind of drag them around. And that's to quite nice effect. So ladies and gentlemen, we went to Maine. The population lives in Maine. And we went to population, and we're going to go down to statistics. Is that okay? Okay, now, ladies and gentlemen. Ladies and gentlemen, we will now put in place two statistics, okay? In that previous model, those who were here for the beginning of the session saw me putting in place statistics on attributes of those people, like their fixed attributes, their parameter values. Here, ladies and gentlemen, we will do something different. We're going to put it into place in their current state. So we're going to say count susceptible. Now, especially those who are here for the beginning part of that session. So again, with a statistic, we give it a name, we specify what type of metric do we want to collect, and for some of those metrics we have to specify over what values do we want to compute that metric, and others over a certain condition. Under what conditions do we wish to collect it? What's the eligibility criteria to be included in this statistic? Okay, so what sort of metric will we be collecting, do you think, here? Is it a count? Is it a sum, a min, a max, an average? What do you think? Look at the names. It's a count. It's count susceptible. Note, reflecting the tyranny of Java, there's no space there. Okay, count susceptible. Okay, and what will be the criteria here? Well, the criteria is going to be, is the person in the susceptible state? Is that okay? Okay, so ladies and gentlemen, what we're going to have to ask is this person in a susceptible state? This condition is going to be asking, is this person eligible? How do we say this person? Well, it tells us. It's called item. Item dot, and what you say is in state. Okay? In state. Okay. And you would say person dot susceptible. Because there might be deer in our model. There might be moose. There might be coyotes. There might be porcupines. And there might be susceptibility for a coyote that's different than susceptibility for a person. For example, to mange or something. I don't think people can get mange. I may be wrong. And youth, maybe I looked a bit mangy at times. But there could be susceptibility with respect to different things. So we have to say susceptible with respect to person here. I think that it will enforce that, but I'm actually not certain of that. It's a good practice, particularly if you're dealing with multiple types of agents, to be clear about which one. So it's susceptibility in person, because remember, it's susceptible in the person state, okay? So I'm going to go back to this. Okay, person dot susceptible. So this is going to count the number of people. It's going to count the number of people who's passed this eligibility criteria. The person is referred to as item. We're asking, are they in this certain state? Okay? And shall we run it? Let's run it. And what we will see now is up here, if you click on population, you will see the number of people who are susceptible shown over time. Do you see that? Do you see what lies before you? Okay. Great. So, ladies and gentlemen, that's good. Now, we've computed some statistics there, but I'd like to take it a bit further. And for those who were here in the first part of the session, those loyal compatriots, I'd like to give you a little bit of an extra reward here. So we're going to go to the palette, and we're going to go to the analysis tools, and we're going to drag in a time plot here. And we're going to plot out the number of people that are susceptible over time, okay? We're going to plot it out. Okay, okay, so I'm going to actually drag it up above this line for reasons that will become clear, and this time plot, and make it a little bit larger, okay? So, ladies and gentlemen, what did I do? I went to main, because I want to see a plot regarding statistics, cross-sectional statistics for the whole population. In the palette, I went down to analysis, and I went down to time plot, and I dragged this in and put it up here at the top, okay? Okay, so are you okay with your time plot? Okay, we're getting close to being done with even that. Okay, ready? For the time plot, we can call it what shall we call it? Disease counts or something like that. Yeah. Okay. And notice in the data items, it has no data items defined yet. We're going to add a data item. Okay. And this is going to be a value. It is going to be called susceptible. Okay. Or count susceptible. And its value, ladies and gentlemen, its value will be population dot count susceptible. Now, how does it know how many people, how does it know what count susceptible is? Who told it what count susceptible is? Oh, let me emphasize something to you. You notice how quickly I typed that. I actually didn't type it all. I started to type population, and I did control space. On Macs, it is option space or command space or alt space, one of those, I think. Population dot count susceptible. Okay, and then control space again, and it filled it out. Filled it out like that. That's very handy. If anyone's using a multilingual keyboard, if, for example, you switch back and forth between English and another language, one thing you may want to do is go up to Preferences, and you can go to Key Combinations, and you can control with what keys you do the code completion, what keys it fills that out for you. So if this is conflicting with one of your keyboard switching things, you can go here and check what it is and record a new one so that you can have it completed out for you. So again, count, you should be able to go like that. Are people having trouble with that? Is that working for you? Yeah? Okay. Okay. Anyone need help with that? Because it's a key asset. I will tell you that probably TA needs and delays in boot camps are they'd probably reduce by a factor of 2 to 4 times if students use this. Control space. So please use it early. Please use it often. Rather than trying to type out things, particularly my terribly long names, just start typing them, control space, and you'll probably be a happy camper because you'll have fewer mistypes. fewer typos. Okay? Typos are the bugbear of TAs for this for these boot camps, and probably 90% of typos to 95% can be avoided by code completion by doing control space. Okay? Who needs help with that? Okay, ladies and gentlemen. So here we've told it to plot susceptible, and we will leave this information for now and see what happens, but we'll go back and fix something up. Okay, so ladies and gentlemen, you should see that, and then up here you should see a plot forming. Okay, so this is counting the number that are susceptible, but you'll notice it's scrolling and awfully quick here. There's a very small range associated with it. So I'm going to ask it to plot at a time, not just about 100, but maybe 500 data points, 500 points, or 500 time units across. So I'm going up to time plot, and I'm going to scroll down, and there's a thing called, under scale, called time window, and I'm going to make it 500 model time units rather than just paltry 100. How did I do that? Let's rehearse this entire plot. Okay, so we started by defining a statistic here in the population. The statistic was called count susceptible. Note the name. And I defined it as such. For each person in the population in term, it calls them item. Item is the first person, and it says, are you in this certain state? No, I'm not. So we're not going to count you. Next person in the population called item. Are you in that state? Yes, I am. Okay, we've got one. Okay, next person state, called item now. Are you in that state? No, I'm not. Okay, still one. Next person, are you in that state? Yes, I am. Count this down, 2. So it's going to be counting up, looping through each person in the population in turn, and checking if they're susceptible. Counting that up. Now that's a service that the population can provide. And guess who's the consumer of this service? One of the consumers is this plot. Because this plot plots out a certain value. And that value is exactly what we defined in the population. This is the statistic. We're asking, give me the value of the statistic in the population. And it gives us back a value. That's what the plot is plotting. Okay, and having done that, we switch down here, and I frogged a setting here in scale to make the time window 500. Are we okay with that? Okay, ladies and gentlemen, let us run this now, and let us enjoy the fruits of our labors, spelled with a U. Okay, so here we go, and we have a count of susceptibles plotted out. Okay? Now, you'll notice, however, that there's one more unseemly thing happening. This is all par for the course, and this is why I try to teach this. You'll notice now we have this nice expansive time window, but it's doing something weird. It almost looks like a snake is making its angular way across our screen. And it's removing part of the graph, even as it draws more. So to sort of give a nod to the AnyLogic tyranny, we need to go down here, and we need to actually go to one more setting. These are 3 standard things you do. You add it in a data item, and then you go frog the time units, and you say display up to how many samples. And I'm going to say display up to 1,000 samples. Why 1,000? Well, okay, actually 500. Okay, 500 because it's updating every 1 day for 500 days visible. So I'm going to display up to 500 items in it. Now I'm going to run it, and we can go up here and plot it out. And now it looks like a happier camper. Is that okay? Now, yeah.
Yeah, no trouble with the actual table displaying with a run.
Okay, so the table, meaning the plot?
Yes, yeah,
okay, and so what is it showing on it?
yeah, just this one.
Okay, oh, got it. Okay, so what you need to do is you need to, sorry, you don't need to do that. Okay, so actually keep it running. The only problem is you need to go scroll up to find it. And on Macs, you need to do like the equivalent of right clicking to drag down here. Yeah, there it is. Okay, there it's appearing. You see that? So if now you can speed it up. So highlight this, folks. You can speed things up by using this button here to turn it into virtual mode, or you can slow them down by coming out of that mode and for example, using this. So you can speed up manually, or you can put it in the fastest possible. Does that help you see it? Yeah, okay. Okay, so ladies and gentlemen, now I want you to complete. I want to get those brains getting some blood at least after lunch. So I'd like you to tell me, now I want this plot to plot out the number infectious over time, or exposed. How am I going to do that? How am I going to have it plot out the count of people who are exposed over time? Can you tell me what I need to do? Sorry? Add.
In the plot.
Okay, add in the plot. Okay, so we'll add a data item here, right? Add a data item. This will be called count infective. Excellent start. And now what do I put here? What did I put up there? I asked the population how many are susceptible. Let's suppose so what would I type? Population, it'll complete that. Then I do count, and there's no count infective. Why not? Or count exposed. Why not?
You need to add it to the population.
You need to add it to the population because we haven't defined that statistic yet. All we have is one statistic. So you'll tell me, what do I need to do in this population to add that?
Go to statistics.
Good.
Add like the plus thing.
Plus, and then type here, count exposed, and then it's a count, and what do I put here?
Item.instate.
Yep. In person, in-state, person, dot exposed. Good. Boom. Okay. Great. Now, having done that, we can now. So let me put it up there. Sorry, So this is the new statistic that we define. Count exposed. It's a count of the number of people who satisfy this eligibility criteria. This condition specifies the condition under which a person is counted or not. Here, they are counted if they're in an exposed state. Each person in the population. First one called item, second one called item, third one called item, etc. Okay? Yeah. So each person in the population is being called an item. Now, this is going through the population. We're defining a statistic. By virtue of defining it, now we can use it up at this plot. So we can ask population.count exposed here, and it will happily fill that in now. Population.count, and this should be count exposed. Sorry. And we can choose the appropriate color to use. Let's use yellow for this, and let's use count susceptible, let's use green. Okay? Great. Okay. Are you okay with that? Okay. Who needs me to show something? I'm happy to show something. Okay? Okay. Should I run it? Would you like me to show you the population? Here, if anyone needs to see the statistics in the population, these are the statistics. We define them, and having done that, it knows how to compute the count exposed, and that's why we can ask it count exposed here. Okay? We ready to try this? Okay, let's give it a try. Okay. Okay, so now we can go up, and we should be seeing two plots, and indeed I see them. they're intertwined here, but there's a yellow and there's a green, which happen to be the provincial colors of Saskatchewan. And they're coming along. Okay, so ladies and gentlemen, we have a nice depiction of what's going on, but more than that, if we go here and we expand the population, if you click on this and you were to run it, you'll actually notice these statistics being computed. So at a given time, we could ask how many susceptible, how many exposed are there, and vice versa. Okay? So we're having some outputs from this that are occurring dynamically. May I show you something else too? If you were to right click on this and you were to say copy all, for those of you who have Excel installed, if you were to go call up Excel here and go create a new workbook, you could go paste in those values. Okay? So those values are actually available for export. Now, there'll be more values available if you save an additional number of data points. This is only going from 2233 to 2732 right now. And it's going, in short, 500 data points because that's all we told it to store. But this is a way to easily export. Okay? Okay, ladies and gentlemen. So a little bit there with the state charts. Things are changing over time. We're having evolution. But let's go and add some texture to this model, shall we not? Ladies and gentlemen, let us go and put in place a few additional states. Actually, let's just do it with, let's put in place a few additional states. So, ladies and gentlemen, I would like you to go create now an infective state. Okay? So, how am I going to go add an infective state to it? Where do I need to go in AnyLogic? If I want to add an infective state to my theory of personhood, to my theory of what it means to be a person, to my sort of natural history of infection with which people are associated, where do I go in the model? Okay, I'm going to go to the palette, and I'm going to add what from the palette to what over here in the canvas? I'm going to add what from the palette? From state chart and add a state. And where will I put it? Into main or into person? Indeed. Okay, so let's go drag it here to person. And this is going to be infective state, right? And its color will be red. Okay? Okay. Great. Okay. Excellent. So this transition is going to be called emergence from latency, becoming infective, and we'll show the name here. Okay, completing latency. That might be another thing, right? Completing latency. The actual completing latency. So they're completing this period where they're merely exposed, not yet infective, and now they're going to start shedding. Completing latency. And we could say how long it takes them to complete latency. For how long they're in this state. And let's suppose that they're in this state for, let's say, 3 days. Okay? 3 days in this state. In general, we would make it a parameter, which we could change, but I want to focus on one thing at a time. Okay. And then, ladies and gentlemen, we are going to put in place a final state that's going to be called recovered. Well, okay, let's leave that out for now. Let's just live with these states, and let's have infective now go to susceptible, and suppose it goes to susceptible now with a rate of 0.1 per day. How long would they be in the infective state on average? If you have a hazard rate of 0.1 per day of recovering, can anyone tell me how long will they be in the infective state on average? It'll be 1 over that. That's the mathematics of it. So if you have something that's exponential, if you have something where your chance per unit time, no matter how long you've been there, if you're still in that state, your chance per unit time of leaving is 0.1. The average time in the state will be 1 over that, or 1 over 0.1, or 10 days. This is a hazard rate, and the average time till that event will be 1 over that hazard rate. That's a fact about stochastic processes and about the nature of the exponential distribution. So they'll be in this infective state for an average of 1 over 10 days. So what do we have to do to make them appear properly infective? Remember, for these two states, color equals green and color equals yellow, they're set appropriately to the color. What is it for infective? What do we need to do? Set their color to be what? Color equals red. That's right. Are you ready? Color equals red. Shall we run it now? Just to see what it looks like? So what I've done is, now that they're infective with this with a rate of 1, they complete latency after 3 days, and the recovery takes place with a rate of 0.1 per day. In other words, a mean time infective of 10 days. Okay, let's run this. Okay, here we go. And I see lots of yellows, and then I see some reds, and then I see some greens. Okay, great. Ladies and gentlemen, so we have people going between all 3 states here. Some people this one's infective right now. It's hard to see because it's red. This one's exposed and is soon going to become infective, etc. And I'm going between different people. Okay, ladies and gentlemen, so we have kind of a more articulated theory of natural history of infection, but something critical is lacking here. And what is it? There's no communication of infection here from one person to another. Is that not right? No communication of infection. Probably we should, though. We'll go add that in. Let's go to main and let's go add in a graph, though, for the count infective. In order to add that graph in of the count of people infected, or to add that line into this graph, what do I need to do before that?
Go to population and get the statistics.
Go to population and set up the statistic accordingly. So we'll do plus here, and we'll do count infective. And what will the formula be? What will the eligibility criteria be for each person called item? Item dot in state person dot infective, indeed. Okay, so this is count infective. So now it knows how to compute the count of people who are infective. And having done that, we can go over to the chart and we can go add in an additional item on the chart. An additional data item. We already have this count susceptible. We have this count exposed. This is with respect to this time plot. And now, ladies and gentlemen, just like that, we're going to create this count infective. And its value, ladies and gentlemen, will be population dot count infective. The count of people in the population who are infective, and we're going to give it a red color. Is that okay? Okay, now, ladies and gentlemen, we should be able to run this model now. and see a number of people infected. We still don't have it being communicated. So who would like me to show one of those things I did here? Here's population. And for population, I defined something called count effective. This is all in the statistics area. I created this thing called count effective by doing this plus to create it. It's a count of the number of people who pass this eligibility test. This eligibility test asking if they are infected, if they are in the infective state. Is that okay? And this graph here, I went to data and I added a data item, and its title is count effective and its value is population not count effective. Is that okay? Shall we run it now just to see what happens? And then we'll make the radical departure towards having communicable illness. Okay, so here we go. There we go. This is plotting the number of people who are susceptible, exposed, and effective over time. Why the variability? Why that sort of noise-like pattern there? Why is there such up and down? Why isn't it all flat lines? Those of us who do compartmental modeling, differential equation modeling, while differential equations can be combined through stochastic differential equations with stochastics, we typically will see for a deterministic model, it's going to give flat lines. Why are we seeing such variability?
Because of the rates.
Yeah, the rates, exactly. So these are not fixed things. Some people, while they're in that state, that same chance per unit time of leaving, but each time they have a kick of the can, and sometimes they connect and sometimes not. So sometimes it goes sooner, sometimes later, and by the vagaries of chance, there's these fluctuations around these points. Now mind you, it's not to say there's no equilibrium of sorts. It's pretty clearly a sort of equilibrium here, but it's a quasi, it's a probabilistic equilibrium. So there's fluctuations around these points. Fluctuations where if it's stable equilibrium, it'll come back to that equilibrium. And it's one of the beauties of compartmental analysis you're not going to be able to get, incidentally. Not going to be able to get with a capital N through agent-based modeling is a sense of whether an equilibrium is stable or not. And that's an important insight. So for those who have ever done it, deriving eigenvalues associated with equilibrium, proving that it's stable can be a very powerful result. It says the system's resilient in a certain sense, if it's a public health system resisting these impacts. Here we're getting these fluctuations around this point, which if the system were unstable could take off. Here it's a stable system. Okay, ladies and gentlemen, here we have these equilibria, but we don't yet have infection spread. I'd like to put it in there. May we do that now? Do we need a health break before doing this? We've come a long distance already. We've added behavior into this model. We have seen a couple different types of transitions. We've shown outputs of data, both to Excel and in the form of plots and statistics. So we've come a long distance, and you're to be congratulated. You'll be patted on your back for sitting through this. But do we need a health break before the final sort of crescendo, where we're going to add networks and communication of infection? Do we need a health break?
Yes.
Okay, short health break? Okay, 5 minutes to steal ourselves. Okay? And now we're going to undertake that summit.